Okay, welcome back. A couple quick announcements. First of all, there's a few people who haven't picked up their midterm yet. You can pick them up with Michael and Ani, maybe in office hours, or we could walk up after class. Another quick announcement is that your project proposals, I will be reading them, and we'll all be reading them this weekend and try to get you some thoughtful feedback. Hopefully this weekend. So, yeah, sure. You can change your project, I guess. But try to send me something, maybe ideally, even something short before the weekend, and I'll try to give you some feedback. Okay. Yeah. Hopefully, I mean, we'll give you feedback in the hopes that we can sharpen or just tighten or broaden the scope, as appropriate, just to try to help you out, push you in a slightly different direction if you're interested. So, okay. Today we get to talk about manipulation. I defined running and walking and everything, so I looked up what the Handbook of Robotics used to define manipulation, yeah? So manipulation refers to the process of moving or rearranging objects in the environment by establishing physical contact and exerting forces and moments. I like that definition. It's a good definition. Okay. So here's the cool thing. The problem formulation is exactly the same as walking. Right? So the picture I drew last time, I'm going to draw it again, right? So I've got a rigid body here. It's got a mass. It's got an inertia. I'll parameterize it in the plane with x, y position, maybe an orientation theta. And I've got some forces I'm going to exert on that. The only difference is I'm going to point the forces in instead of out. That's not a major difference, right? That's just a sign flip. F1, F2, F3, let's say. And my goal is to take some initial pose of my object. Maybe and of my robot. We'll call this, let's just get some notation out. Look, I'll call this Q object. I might just write QO later to be shorter. And Q robot. Possibly just QR later if I'm going, yeah. And move it to some target position. Say Q desired object. Maybe I don't care where the robot ends up, but I want the object to have moved. Yeah? So now, this time, we started off with magical thrusters off in the air that could move. Then we revealed the secret that they were actually legs. This time, maybe they're not legs, but they're fingers. Okay? But really, the higher order bit is that if you know how to do walking robots, you already know how to do manipulation, right? That's a little jab at all the manipulation people in the audience here. But and the manipulation people say if they already know how to do manipulation, then they know how to do walking. That's less. I don't know. That's also something you could say. I guess the problem with both of those statements is that we don't really know how to do walking or manipulation. So the transitioning from one to the other is still tough. Okay, but the problem formulation really is shockingly similar. And we're going to see that there's a few places where the abstractions we used, for instance, in the last lecture, are going to be the same abstractions that are helpful in manipulation. For instance, this model as a single rigid body exposed to forces and separating the problem of reasoning about the forces, planning the forces first possibly, and then reasoning about how your robot has to generate those forces. You can sort of separate the problem the same way we did in the walking, the most recent walking lecture. Worry about the kinematics of the leg in a second pass. First, let's just plan where I'm going to put my forces in the world. That analogy moves over nicely into that's very similar to what you see in the manipulation world. There are some notable differences, not so much differences in the problem, because the problem is the same in many ways, but sort of different focuses, things that the manipulation problem brings to light that the walking people haven't worried about so much, and vice versa. So let's say, different areas of focus. So, I'd say one is that the idea, so last time we tried to sort of decompose the problem, like I just said, into planning the forces and then worrying about the kinematics. I would say the division of kinematics and dynamics in manipulation is in some sense even more complete. You can actually, people are very successful doing a lot of work in manipulation without thinking about anything about the dynamics, because you can sort of separate out, the dynamics don't come into play until you actually start making contact with the object, and a lot of maybe the hard kinematics problems of avoiding the world and everything happen before that. And you can decompose these even more completely. Okay, a second sort of, when you do get into the dynamics of manipulation, another sort of different area of focus is that the manipulation community tends to deal with more sort of richer contacts, more contact with more complicated geometries than the walking. I mean, with walking, I'm sort of happy to say I've got sort of my heel's going to touch the ground, my toe's going to touch the ground, and that's good enough. And I'm not really worried about walking on non-convex surfaces where I might rock or over. I mean, some people are, but the bulk of the community has been able to get away without dealing with really rich interactions. If I wanted to, I don't know, do an earthworm kind of behavior on the ground with my robot, where my elbow's touching, my knees are touching, my belly's touching, all these things, then that could be a richer model of contact. But in walking, we've gotten away with sort of having a few contact points, and they're mostly hitting, flat-ish ground so far. In manipulation, that doesn't feel as true, right? So in manipulation, I could manipulate things by just touching only with my fingertips, but typically the objects are non-convex from the view of the robot here, and I tend to have more sort of richer grasping. I might touch with the whole geometry of my hand might be touching, or might be touching in more sort of complicated ways. And so the tools from manipulation have dealt with the geometry and even some of the dynamics of contact in richer ways. So sort of more contact and richer models of contact. So I might worry about a cylindrical finger interacting with a cylindrical cup. And in walking, I would have just said it's a point that touches the ground, right? And we'll talk a little bit about both of those today. There's a third one that I won't get to yet today, but we will talk about before the end of the class, which is that in manipulation, there's a big focus on uncertainty, right? So in manipulation, I tend to be picking up things I don't know everything about, right? So I might not know the exact geometric model of this thing. I certainly probably don't have a perfect estimate of its a moment of inertia. If the thing I'm controlling in the walking case is my robot, then I might have taken the time to build a fairly accurate model, and so my uncertainty is less. Of course, there's uncertainty in the terrain, but the focus has been in walking more on the stability problem, right, of balance and things like this, whereas I don't really have to worry about the stability of my hand. I worry a little bit about the stability of my object, but it's simpler. And in the manipulation, relatively, they're worried more about uncertainty, about dealing with the different types of uncertainty. And we'll at least talk a little bit about the tools there when we get into the estimation and statistical modeling kind of questions in the class. So there's more focus on uncertainty and relatively less on stability. But of course, uncertainty matters for both problems and stability matters for both, and there's crossover. Okay, but just culturally, there's been more people talking about uncertainty in the manipulation world. Okay, so let's see some of the implications of these. So I do think that there's you can sort of get farther in manipulation without worrying about the dynamics. I think if you wanted to start doing human-like manipulation, then I do think you need to think about the dynamics. And by the way, the dynamics are sort of underactuated by definition, right? So I've got an object in the world, it's got no motors, no actuators attached to that, and I got to move it around, right? So the dynamics are interesting because they're underactuated, right? Okay, so there's sort of a standard decomposition that most people take. So the screen's cutting off a little bit today. If I write off the side of the screen, remind me, but I hopefully I'll remember. Okay, so if I have my robot in the world and an object I'm trying to manipulate in my robot hand, I don't know, it's coming in. That's a small hand in a big box, but we'll see how we do. Okay, so my robot hand's coming in, and I've got to manipulate this box. Right? A standard approach would be to first examine or pull up a model of that object, and the first thing you'd often do would be to try to decide how I'm going to grasp it. So figure out in what configuration I'd like to be once I've grasped the object. So that's often called grasp synthesis. Okay? And a lot of times that's done almost independently of the complexity of the arm, but you're just thinking about if I was going to put fingers on that object, where would I like to put those fingers so that I can get a meaningful grip on the object, right? Okay, given that, the next step would be you start worrying about the robot. How am I going to get the robot from wherever it is right now to that desired contact position with the object without knocking it over, without bumping into things in the world? And this is the place where you can really sort of get away. If you have a fully actuated robot that's about to do the manipulation, you can get away with doing basically a kinematic trajectory planning. Or you might even say pre-grasp location, to just before I make contact. And then, sort of, this isn't completely fair, but it's fair. So I think what you do then is once you get close, you've done your nice planning, and you've got yourself sort of close. You close your eyes and you go like this, and you hope that you ended up where you thought you were going to. That's pretty much what everybody does. It's the truth. So there's a sort of step 3, which is execute the grasp. And if you think about what you could be doing there, right, you could be building hybrid models. Think about the impulsive event when your first finger hits the ground, hits the object. Your second event, that's what people are not doing. They're basically getting in the pre-grasp and then going and hoping that you get to where you hoped. Okay. And then there's another rich sort of planning problem afterwards, which is to plan now a collision-free path with the object in your hand, let's say, to get through the environment, to get wherever it needs to go. If I had to move it through a world that had some other obstacles in there like this, and I had to move it over there to get here, then I've got to worry about moving, not colliding with the object as well as the hand, right, to get there. And then you kind of, again, hope for the best, let go, release your grasp. And that works pretty well, although I would say we still need a lot of work in manipulation in general. There's beautiful work out there, but robots are still struggle to do general manipulation, as there's lots of people in the room that are working on it. So this is a very standard decomposition, and what it means is actually there's really strong research groups out there working on manipulation that actually focus mostly on the kinematic parts of this and dealing with the uncertainty about the object, the perception of the object, and all these things, and don't really think about the dynamics part. There's other research groups out there that think a lot about grasp optimization, grasp synthesis, the contact dynamics, and focus less on the kinematics. Okay, and culturally, that it's somehow become more separable, these two problems. So I think that's, I don't want to do that, right? I think you guys are going to have the tools to solve the whole problem at once. Okay. Every one of these has lots of potential details. We'll just discuss a few, and I'll emphasize the dynamic ones because I like dynamics. But for instance, the type of details that I'm completely leaving out today are, this whole examine the object, estimating the pose of the object. That's hard. That's really hard, right? Lawson can tell you how hard that is. That's a problem that I'm just going to pretend we don't have to solve for the moment. Okay. Estimating the inertial properties of that object, that could be a hard problem too. There's all these sort of details that I'm going to sweep under the rug for now, so we can think about the dynamics and control part of it. Okay. So I won't say much about kinematic planning, except to say that the tools we've already talked a little bit about with trajectory optimization can go a long way towards doing kinematic planning if you like, right? So there's lots of ways to do this, and we'll talk about other ways. But for instance, one set of solutions that people really do use is trajectory optimization. Right? So you guys know enough about it that I can just give you the idea very quickly. If I were to just say that my dynamical system was that I have direct control over the velocity of the object, right? And I have a bunch of kinematic constraints now, right? So I have a function that is the kinematics. It can tell me, for instance, the position of the hand or finger 1 or finger 2 is just some function of my robot configuration. So this is my robot configuration, right? Right, then I can start, given that function, I can start writing down kinematic constraints that I can add to my trajectory optimization problem, like maybe the fingers at time of pickup, at the time of the grasp, let's say, need to be at the predefined grasp points. And that's a constraint that you can just write down. It's a nonlinear constraint in general. Okay. And I could say, for all time, avoid collisions. It's another hard constraint to deal with, but you can put it in as you can put a differentiable version of that constraint into my solver and do trajectory optimization with that constraint. You can add joint limits and the like. All the kinematic properties of your manipulator can probably be thrown into a nonlinear optimization for trajectory optimization. And this will work. This will work well. I mean, we showed a few videos of Atlas reaching around a corner and grabbing an object, right? This actually works. If you guys have seen some of the robotics research talks that have been coming through over the last couple weeks, at least two of them, Anka and Sergey, both had trajectory optimization as a major theme in their presentations and for manipulation, right? The two manipulation talks we had most recently had both had trajectory optimization being the back end for the planning. It happens. That's perhaps if I were to take a random sample of manipulation talks, that wouldn't be true, but it just happens that the last two did. And people really do use this stuff, okay? They'll formulate it a little differently than we have here, but it fits right into the trajectory optimization framework. Okay, so the only point to make about this is to remember that the trajectory optimization is not guaranteed to succeed, and that's particularly true in the sort of the manipulation around obstacles case, right? So if I have some goal finger position, let's say, and there's some, let's say, an obstacle here, and my robot is currently over here, right? And I'm trying to get this point over towards the goal. My trajectory optimization will try to make changes to pull this towards the goal. It'll run up against this constraint. It'll probably say I'm stuck, right? And it's relatively, you have to do something more dramatic to tell this thing, oh, nope, stop, try over here, right? So there's limitations in these, but given a good initial guess, in particular, even one that's sort of in the box, they're pretty good, but they're not perfect. They're not going to be able to get out of local minima. Now we're going to generalize our tools and talking a little bit about the randomized planners that make this more complete next week with a particular eye on dynamics, but I just want you to remember that that's a limitation. Okay, so let's think about the grasp synthesis and grasp feedback part. Okay, so given an object, let's say I have like I said, I'm just going to imagine I have a good kinematic model of the object. Given the object, how do I decide where to grasp? Okay, so let's just say I've got a square object here, and I have a few fingers that I get to place. I'll put them something like this, maybe. I don't know. How do I pick where I'm going to grab the object? Right? That's the grasp synthesis question. And there's a couple really important ideas there that you should have an understanding of. Right? So one of the early ideas was the idea of form closure. For form closure, I'm going to need a few more points here. See, I've got a 5-fingered hand. All right, so form closure is the property that if I were to take my current object pose, my current contact positions, that any changes in the pose of the object would result in a violation of one of the contact penetration constraints. Okay, that means I've got my object surrounded, and in a formal way, any change in the current configuration of the object is going to result in a violation of one of those constraints. Okay? That's going to turn out to be a very practical, useful definition, very easy to work with definition. That's going to say that I've somehow caged my object, right? So I make any object rotation that's not 0, any change, then at least one contact. Constraint is violated. Okay, so let's think a little bit about how we write down those constraints in a way to make this an algorithm, let's say. Okay, so at every one of these contact points, the surface has some shape. The most important thing I care about right now is the normal vector of that at that contact point of the geometry of the surface. Okay. Call it Ni for normal at contact I. And I'll call these contact points Pi. Okay, and if I need to describe the contact point relative to the coordinate system of, in the body frame, I'll use the Ri that we've been using before. Okay. So how can I write down a contact constraint given that notation? The sort of non-penetration constraint, I could write it down as saying that whatever my object's doing, I can be potentially moving given if I have an object around a single contact point. Right. Any most motions of this object are allowed, but the thing that's not allowed is if P dot I and N dot I, these things had better not be going through each other, right? So I can write that as the dot product between the point P dot I and N dot I. Oh, sorry, it's greater than 0. Huh? Silly. If I have an inward-facing normal, then I want my P dot I's to be always that way, yeah? If I had a P dot I, then I'd be in trouble, right? Okay, so I want this vector and this vector to be going in the same direction, yeah?
One single frame PIs.
Sorry?
The points DI, are they like
in the world frame? Ri, so I'm gonna define Pi as, you can figure that out from the kinematics by looking at my object and then that Ri vector. Yeah.
So if I grasp this object and a normal that way and a normal that way, and I move the object like this, then on one side.
So right now the contact points are going to be fixed in space. The robot is not moving right now, and the question is just, what can I do to the object? Or, if I'm holding the object right now with these points, could you come up and move the object on me?
So the robot's
Yeah, the robot's fixed. Okay, so I can define p dot I here by taking the derivative of that kinematics, right? So I can partial f partial q times q dot of my object, and this thing is well known as this thing has a name. We always use it. It's the kinematic Jacobian. Depends on q and it depends on r. Times q dot. Thank you. Okay, so our goal here in life is to pick these RIs so that we can make sure that this property is not violated, right? We'd like to somehow, and the first question would be, can we even check? If I give you a bunch of contact points, can I check if you have a form closure, right? So plugging that in, that's checking a bunch of conditions. You know, if I have this now, J, Q, Ri, Q dot, greater than or equal to 0, right? This condition had better hold for all of the i's, right? I don't know if I want the I there or not. It's completely defined. For the case of them all being on the same body, it's okay to not have that.
Sorry, why is there no dot?
Because I've assumed it's constant.
But I mean, the body is not.
The Ri is the point relative. Oh, I see what you're. Okay, this is a statics analysis, right? But I'm going to say that I'm looking at the current points Ri, which are defined on the relative to the body. Yes. Can I cause an orientation change? Yeah. So this check for whether given a change in my Q, do I get a change in my, do I get a penetration constraint, is just a linear equation in Q dot.
This check is, this needs to hold for all QIs that has to exist in R. Such that that's true.
Well, I'm going to, right, so every one of these is a constraint. Right? So say what you said again.
So I thought it's for all Q dot. There must exist one.
I'm going to get to that.
such
Yeah.
it's-
That's true.
They don't all hold simultaneously.
Okay, good. Yeah. Right. So yeah, exactly. Okay, good. So Michael's saying that for all Q dots, we would like that at least one of these is violated, or that at least one of these is active, right? That you would have to violate at least one of these. Okay, so the magic here is that these kinematic conditions are all in the velocity space, are all linear in Q dot. So this check is a check on the conditions of a linear set of inequalities, and it can be written down as a linear programming problem. Okay, or in fact, in this case, you're just looking for a degenerate solution of a set of linear equations. So if you write down a whole set of equations like this, a Q dot has got to be greater than or equal to 0, then it turns out that the rank of this matrix here you need for this to be an over-constrained system to imply that Q dot must equal to 0. Okay. The thing I want you to take away here is that it's a linear programming problem. And that there's some cool mechanical insights that come out of it. Because it's a rank condition on a set of linear equations, I can tell you, for instance, that if it's in the plane, and my configuration Q is defined by 3 numbers, x, y, and theta, then for this rank condition to be satisfied, I need at least 4 points on my body. I need whatever, if my Q dot is dimension 3, I need 4 points on my body in order to have any chance of having a form closure. That just falls right out of the equations. And actually in 3D, Q dot has got to be 6-dimensional, so I need actually 7 points, 7 contact points to be able to definitely rigidly constrain the system in a form closure. Okay, and that's I mean, I guess you can sort of see that it would be hard to achieve a form closure on something like this with only 3 points, because I could slip it out this way. It's sort of easy to see. Maybe the 7 points in the 3D is harder to see. Okay, but you can also, this also sort of helps you see the limitations of the analysis, of the form closure analysis, because I'm pretty sure I can hold this object with 2 contact points. I mean, if I could approximate it with 2 contact points, right? So what's the big thing that this analysis is missing? Friction, right? All right. So the next step is to put in friction. Sorry, that was rougher going than I expected. Okay, so the generalization of this idea is force closure. Which generalizes it to allow friction. And in general, thinks about the forces involved with the contact points. Okay, so we're going to do the same trick that we did before when we talked about the walking example. If I've got forces being applied on my object from lots of different directions, I want to be able to summarize them. I can always summarize them with their total influence at the origin as a set of as a sum of forces and a torque, as a single force and a torque applied to the origin, right? So we're going to write down the wrench, the grasp wrench, which is the forces in the x direction, y direction, and the torque around the origin, which summarizes all of the contributions of the existing ones, right? So I can always take all those forces and summarize them as a single force and a single torque, right? Or it's 6 elements in 3D. And the equations to do that are simple enough. You can just take all these forces, sum all the x elements, sum all the y elements, do the cross product to get it to get the moments. That's what we did last time. I'll write it in the Jacobian way, in the virtual work way this time, just because we're using we just introduced Jacobians in the last idea. So I can always write this wrench as the sum of the Jacobian that I just wrote down times the force at the ith element. Okay, in the plane, that's going to be exactly the sums that I just talked about. All right, and this is, in general, the relationship between torque and force through some kinematics is this notion of virtual work. well-known property from mechanics. I can always use the Jacobian to map between, let's say, an endpoint force and the torques at each joint. Okay, so this is just a way to summarize the contribution of all of my forces as a wrench on my origin, let's say. Okay, but now I'm going to start adding additional constraints. I'm going to say that these forces have to be similar to the normal, but they can be in some cone around the normal if I want to use my Coulomb friction. Right? So for instance, the way I wrote it last time was I said that F parallel had to be within some coefficient of friction of the perpendicular, of the normal force, right? That's going to be my friction cone constraint. And if you give me the current positions of the points, if you give me all the contact points and the coefficient of frictions at those contact points, which again, that's a big assumption, is knowing the coefficient of friction of the object I'm about to manipulate. Okay? Then I can try to find, by virtue of this, a feasible F that will, if you were to give me some wrench that is resisting, I can ask, is there a force that satisfies these equations, a set of forces that satisfies these equations, satisfies these constraints? And that's another simple optimization problem, okay? I can try to find Fi, whether it exists, or I can even optimize Fi. In the case of in the planar case, or in the linear approximation of this constraint in 3D, it's a linear program. And if I want to use the true friction cone in 3D, it's an SOCP, a second order cone program. They're both convex optimization problems. Okay, so if you tell me you want to produce some wrench, and I want to say, let's find the minimal forces required at each finger to try to produce a certain wrench on the object, then I can write down an efficient optimization for that. Okay? That also gives me some notion of stability analysis, right? If you were to say, if I want to do a feedback control, and I can estimate someone comes in, or gravity, or whatever it is, or if I'm moving this thing around and there's some external wrench on the object, I can ask the question, is there a set of forces that I can apply, given my current constraints, that would produce exactly an equal and opposite wrench on the system, to therefore resist that perturbation? Okay? So these are sort of the easy problems, is when the contact positions are known, the forces are unknown, then I can ask questions and get good answers. Okay? And the force closure analysis, it's more general than the form closure, with having included friction. So there's some sort of interesting cases you can think about here. So let's say I've got an object in the plane like this, and I've got just 2 points and a friction cone like this. Can I give a force? Can this thing be in a force closure, right? Is this a force closure? Can I resist arbitrary perturbations of this thing? You're limited by your friction cone. So could you imagine a force or torque I could exert on the object that would pop this thing free? Punch it sideways? So this one is actually a force closure because the thing I haven't modeled is I haven't modeled any limits on the forces that I do. So I could squeeze infinitely hard, and as long as those things are lined up and I'm just squeezing them together, then I could actually produce arbitrary frictional force in the side. Okay? So by this analysis, this is actually a force closure, just because I can squeeze the heck out of my object. Right? This one, on the other hand, if I were to have contact points like this, then obviously there's a direction I can push for which I cannot resist, right? If I can only push on the object. Okay, so the force closure analysis still has, it gets harder if you try to model limits in force, whatever, but by definition of force closure, this is a force closure, and this is not a force closure. Yeah?
The coefficient of friction is what determines how wide the cone opens, right?
Yes.
If you had a really high coefficient of friction with the other one, would the cone maybe span an area where you could?
If you were to, yeah, I guess all you need is some direction. If your friction cone gave you any ability to produce a force like this, then that would be. Then I guess you could. No, but still not, because if I push harder in order to make that that frictional force, I'm going to shoot it out that way, right? Yeah, that's a good thought experiment, right? So he's asking, what if my friction cone went like this, so wide that I could produce a horizontal force, but in order to produce that horizontal force, I'd have to push so far this way that I'm just going to shoot this thing out the side. I think that's right. And it shouldn't. I mean, you shouldn't be able to hold something like this against arbitrary force, right? Okay, so all right. So here's the takeaway. So it's interesting that in the grasping world, I think if the contact positions are known, then a lot of analysis is easy. And optimization and even force optimization are relatively easy. But if I start asking, how do I pick, let's say, the number or the location of contacts, then it gets to be a hard problem in general, right? So there's good algorithms and good heuristics that work, including some by Tomas, that for polygonal obstacles will give you ways to check all the possible configurations to try to set up to optimizations. But in general, you get into a much sort of uglier optimization problem or an algorithmic search to find those possible contact points. And another thing that's sort of interesting is that people aren't talking about this quite as much as they used to, because there's been this trend now in building hands that don't quite subscribe to this philosophy or don't even maybe work well with this philosophy, right? So there's been this trend in underactuated hands now, right? Have you guys seen underactuated hands? I pulled a couple. So this is the one we have on Atlas. That's just a simple grasping motion in our simulator of Atlas. But it's actually only got one motor at the base, and it's got 4-bar linkages spread through the fingers, and even springs, so that when it closes, it naturally closes its hand. But it also will do that even in the presence of an obstacle. It'll bend at a different place, right? It'll take the obstacle and then find a way to wrap around and make that closure. So it's sort of changed the philosophy from having this precise grasp optimization initially to like maybe encourage this sort of get up close and then grab and hope for the best. And the extreme for this is, have you seen this universal gripper from U Chicago and the like? This is, they call it the coffee bean gripper, okay? It's basically a bag of coffee beans or sand, or it's a granular media, okay? And they use a jamming phenomenon of the granular media to make this thing go from soft to when they're ready to grab it, it turns hard and grabs basically anything, right? Right, so what's the motivation of doing all this? It's a light bulb, okay, raw eggs. Is that awesome? Glass of water, right? And there's a bunch of different sort of hand technologies that are sort of going in the direction of having less kinematic accuracy but pretty good dynamic performance. Okay, so where does this model of doing kinematic search and then grasping, and then some grasp optimization, grasping and then moving it around, when does that break down? It actually works fairly well, but it breaks down in a couple different situations, right? So that's going to break down, for instance, if your object that you're picking up is really heavy compared to my robot, that's going to make it break down, right? So right, so here's the robot weightlifting champion of the little humanoid at the Fira soccer competition, right? So this guy cannot safely assume that he can't just do kinematic planning and then start assuming that he can just move this through the world. This guy, the object he picked up has massively changed his dynamics, and he has to worry about it. Okay. But there's other places where that assumption breaks down, which is when you start getting fancier with your manipulation, right? People don't just pick this thing up and move it rigidly, right? You guys might be already flipping things in your fingers and doing all these dynamic regrasping type things. So there are a few robots that can do tricks like that, okay? This is my favorite. We actually had a visitor from this lab, Nori, that came in and worked with us for a little bit. This is dynamic regrasping, and this part here has got to be one of my favorite robot videos of all time. Okay. It gets better, right? Here's the high-speed version. So the way they did this is with super high-speed vision. They had a vision algorithm tracking the blob, a red blob that was the phone, on FPGA-based cameras shooting at incredibly high rates. They basically hot-wired their motors to produce enormous amounts of torque in a very short amount of time. And if they were to run it for a long time, it would melt down their motors, but in bursts it was okay, so they could move, and they had this extremely fast feedback loop to do that kind of sort of active grasping. All right, so those are problems where you can't sort of completely just separate out the dynamics from the kinematics, and those are the fun problems. Okay, so let's try to be a little more bold. Let's go more towards this type of work and see if we can think about solving the dynamic and kinematic problem all in one shot, right? So we've already been talking about trajectory optimization. Why not try to do trajectory optimization with the initial problem that just says, I have a dynamical system, there's some dynamics of my object, there's some dynamics of my hand, My initial condition is that the object's there. My final condition is the object's there. Find a solution, right? What's preventing me from doing that? It turns out I don't think there's a lot. I mean, I think it's computational. You have to write it down the right way, but I think we're at a place where we can start writing down those problems, and people are starting to solve them. Okay, so let's be a little bit more aggressive. We'll solve directly the initial problem. Given my q double dot robot and q double dot object, my initial conditions of my object and my robot, find a trajectory subject to all the dynamic constraints and my Q object finals in some goal position. Okay? How are we going to do it? We've got a system that's making and breaking contact, right? So we could try to do hybrid trajectory optimization, right? We could write down the event system, which says my first finger comes in contact with the object, my second finger comes in contact with the object. Each of those has a guard, a reset map, right, and so forth, so on and so forth. And I could write that problem down. We've given you the tools to write that problem down. But you don't want to write that problem down, because that means that somehow seems like the wrong thing to do here, to somehow have to specify the order in my program. Remember, the trick for writing those down is I just say that this guard happens first, then this guard happens, then this guard happens. I'm going to allocate this many points in my trajectory to this hybrid mode, this many points in my trajectory to this hybrid mode, right? So if I have to somehow specify that my thumb comes in contact first, my finger comes in contact second, maybe the inside of my hand comes in contact third, that just doesn't feel like the way I pick up a coffee cup, right? And it turns out, because, like I said, there's been this emphasis on more complex geometry and dynamics in contact with the grasping people and the manipulation literature, they've also come up with better ways to write down those dynamics, or they've touched different parts of sort of contact mechanics to write down and even simulate those dynamics. Okay, so if you look at simulators today, I see what happened. I wrote on my slides. That's why I keep flipping. I wrote on my slides, and so they both look like they have content. Aha. I don't know which one is which now, but that's the whiteboard I see. Okay, got it. All right, so if you look at simulators today, this is this is Bullet. It's one of the simulation engines people use in robotics. Okay, Bullet's in this case simulating 4,800 bricks falling on top of each other. Just think for a second. The way we've told you to do simulation so far is that you write down every hybrid event and hybrid guard. You simulate until you find an event. You stop. You do your reset map. You go on. You don't want to do that for this, right? People don't do that for this, right? So there's got to be, in order for them to have simulated this effectively, there's got to be another way to write down the dynamics that makes it sort of computationally tractable to do something like that. Okay, so what's the way that people do that? Anybody know how people simulate that? There's sort of a 3-letter acronym that should come to the tip of your tongue if you know it.
Discrete element model.
There are discrete element models that use. I mean, it's similar to that, but that's not the 3-letter acronym I was looking for, I guess. But if it was particles, then yes, I would say people do exactly that, and they're going to write down a lot of the same constraints. But there's a piece in the middle that's required to make it work, to handle all these non-penetration, collision events, and everything like that. They're called LCP solvers. LCP solvers, linear complementarity problem. You're going to understand in a few minutes what that is and how we're going to maybe leverage that to solve the planning problem. Okay? All right. So let's think a little bit about how we're going to simulate contact. Let's see if we can do the same trick to make planning through contact work. All right, so let's say I've got a simple example here. I've got a brick that's falling down, and let's say it's got a potential contact point as it's falling here, okay? Then one way to write down the dynamics would be to write down the dynamics as if that contact point always has force on it. In that case, my equations of motion would look like this. If this was a whole robot, it would still have the same equations of motion, right? I have my manipulator equations. If I have a robot with inputs, I might have a BU. But then I have new forces that are being applied to the system. Call this guy Fi. Then I have some new terms. I guess I'll leave it in new. State-dependent terms that bring in my forces Fi. Okay? So if I can compute what these forces are, then I can plug it into the equation and I can simulate it pretty easily. Okay, so how are we going to figure out what these forces are? Well, we're going to need at least one extra working variable, which is let's describe the distance between the contact point and the closest object in the world as some other state-dependent, configuration-dependent quantity phi. Okay, so VIQ is the distance, signed distance, let's say, to the nearest contact. So I want it to actually go to be negative if I'm inside an obstacle, and positive as I'm away, in a way that is the distance between the potential contact points. Then I can write down the constraint on my force in the same way that I've been writing down so far. I can say that the forces that I have to solve for have to satisfy the constraint that the perpendicular force at that contact point has to be either that has to be 0 or phi has to be 0. I should say this is the no force at a distance. This thing is called the complementarity constraint. It says you should think of it as saying that either Fi equals 0 or VIQ equals 0. Again, I can put in other constraints too. I can say, for instance, my friction cone constraint. I can say that my friction has to be, I can only have normal force. I can put a constraint on the force. I can say that this penetration has to be greater than or equal to 0. Okay. So if I can solve a problem here, which is find forces which satisfy all these constraints, okay, then simulation is easy. And it turns out that finding a force that satisfies all these is something I can do with all the optimization kind of tools we've been talking about. In particular, with this complementarity constraint in the middle, it becomes this linear complementarity problem, or it's a complementarity problem in general. And if I make a linear approximation of my friction cone, it's a linear complementarity problem, LCP. And specifically what the LCP can give me is I can find a pair Q double dot F which satisfies all these constraints. And it turns out this is a problem that I can solve quickly and efficiently, okay? To the point where, this is the big idea here, we're actually going to solve this problem on every time step of the simulation, okay? So finding the forces that I need in order to simulate, if I could find the forces, it would be easy. If I even knew which points were in contact, it would actually be okay to find those forces. But figuring out, in general, in these complex context situations, what the force is, given what's actually in contact, what's an active force, what's not an active force, turns out to be really hard, but it's something we can solve efficiently with an optimization. Okay, so when Bullet is cranking away, simulating thousands of bricks, on every simulation time step, it's not just computing an Euler update of a closed form solution, it's actually computing, solving a small optimization problem. And then that's how you compute the next time step. Okay, so really the dynamics of my system are solve an LCP given the dynamics of my current step and my torque inputs. Okay, every simulation time step I'm solving these small problems. There's a subtlety inside here. Okay. The simulations always do discrete time steps before we've written down continuous time dynamics and then done Euler integration or something to get to the next time step. There's a subtlety in here in the contact world about writing down the continuous dynamics like I wrote down here. Okay, so let's think about what happens as I drop my brick. Okay. What's happening to the force? So as I'm dropping my brick, my contact is not allowed to be, my contact force is 0 in the air. 0, 0, 0. When it's on the ground, it's whatever that force needs to be to make sure that this point never penetrates the ground. So it's resisting the object. It's producing a force to resist the ground. But at the moment of impact, something harder is happening. I have an impulsive force, right? My velocity of this point and therefore this object changes instantaneously. So I actually get an infinite force that does finite work over that interval, right? It's an impulse. It's a delta function of force. Okay? So simulating things with infinite forces, it doesn't seem like such a good idea, right? Asking optimization problems to find solutions with infinite forces doesn't seem like such a good idea. It seems numerically bad. So the way you get around that is you do an averaging method, a time-stepping method. It's called a time-stepping approximation. Which computes, given my continuous dynamics and a discrete time step, it finds it finds an xn plus 1 and the forces required, but they're time-averaged forces. That's off the screen, isn't it? Okay, and that gets around this gross issue of infinite force over impulsive forces. I do a time-averaged force. So I can ask the solver to say, give me some time-averaged force over this interval so that when that interval's done, all of these constraints were satisfied. Okay, and this is the time-stepping method for simulation, and it's typically solved as a linear complementarity problem and optimization. Okay, so that's a big idea. I'm actually going to describe my dynamics as an optimization problem. not as some closed form thing. Okay? So here's a proposal for, for how we can be doing manipulation with trajectory optimization using this idea. This is Michael's proposal. He wrote a paper in 2012 about it. I don't know if he's bold enough to give it as assigned reading on the website. I'll give the reference. Okay. So here's an idea, right? So let's do our trajectory optimization. Okay, we're going to discretize time. We don't have to do simulation anymore. We're going to solve for the entire trajectory at once using our direct trajectory optimization. And let's list as decision parameters x at each of the time steps, u at each of the time steps, my control input, and also the contact forces at each of the time steps, and plus some additional slack variables for friction and the like. Just happens to be the right way to write it down. Just have some slack variables there, okay? And then I'm going to put in to the optimization the extra constraints, not the linear complementarity problem update, but just the original update, because I know what f is here. I can just write down my discrete time approximation. Of what the force is going to, of what the update's going to be given I know the forces. And I'm going to ask the solver to find a trajectory that's consistent with the forces it's guessed right now, a solution that's, but also with all the contact complementarity constraints and the like. Okay, and instead of solving this with an LCP solver, we'll just solve it with SQP, right, with our SNOPT, hand this to SNOPT. And the same way that the optimization is working at simulation time to solve this problem, we'll let the trajectory optimization solve this contact problem at optimization time, and we'll let SNOPT do all the work for us. Okay, so our dynamics, again, are only enforced by this optimization. That is the trajectory optimization way. But we're going to explicitly make the contact forces part of the decision variables and let the solver do the work. Like the LCP simulators, this has the advantage that we can use the time stepping idea to come up with average forces and get rid of the impulsive events problem. Okay. Like the LCP solvers, so we don't have to schedule a set of modes that the system's going to go through. I don't have to somehow tell the system first make contact with your finger, then I have to make contact with your thumb, and so on and so forth. I can just ask it to find some forces. And the only big question really is, can the solver handle a problem of that complexity and do something interesting, right? And it turns out there's some sort of cool, subtle reasons why it does, why it's an interesting way to write down the problem. Okay, so I see everybody writing. Maybe I'll try to use the corner instead of flip to the next page. So let's say I have my hand up here. And my object of interest down here. It has to be moved in the environment. One of the problems you'd have if with a standard trajectory optimization approach to this, even a hybrid trajectory optimization approach for this, if you said I want the object, if my goal is to move the object over to here, okay, the solver by default would have no way of knowing, if I didn't have the force as a decision variable, then it would be very hard to somehow tell the solver that you need to go out and reach and touch this object in order to start pushing there, right? If I were to take if the nominal guess of the robot is to move here and the object doesn't move at all, if I take the gradient of the current performance and look at the cost, there's nothing telling me that I'll do better if I go down and touch the object, right? There's no gradient telling me to go touch the object. In this formulation, it knows immediately that if I want to move the object, I need to produce some force this way, right? And then it's got to do something. It's got to make somehow this consistent with the trajectory of the hand. So it actually has a signal which says, well, this object, in order to move over here, is going to need force like this. And in order for this force to satisfy the dynamic equations, it's going to have to be in contact with this. And it'll actually pull the hand down in order to, there's a signal that will make the solver understand that it has to make contact in order to do the optimization. Okay? And furthermore, even though when at intermediate points you have this sort of force at a distance because you have these as separate decision variables, once the system has been solved and this constraint has been satisfied, you won't have any force at a distance. Right? So it's sort of a magic way to allow force at a distance while the thing's thinking about it in order to tell it, give it a signal on what to do, but still have no force at a distance, have a dynamically feasible solution when you're all done. Okay, and that works well, and that's what we've been showing you examples of making, of picking things up. In fact, the talk by Sergey Levine the other day, he used a form like this, and he was showing his simulation jamming things in peg and hole problems and stuff like this. He used a formulation like this to make that happen in the robotics talk. Okay, so this, I think it's an idea that works, and people are using it. Good. So really, the high level bit is that if you know walking, if you know how to control a walking robot, then you know everything about manipulation, and vice versa. To be fair, if you know manipulation, you know a lot about walking too, because they're really almost exactly the same problem. You just put a little more uncertainty in the manipulation problem and a little more stability focus in the walking problem. Cool. Okay. See you next time.